thank you for coming again, particularly YouTube. So I will talk about the fault tolerant clustering in scientific workflows again. So here's the outline. First, I will give you some introduction about the workflow and the model that how we model the failures, and then we show the necessity to do the fault tolerant clustering, and later we'll show the experiment with two workflows, and then we'll talk about some specific failures such as the test specific failures and the location specific failure. So workflow is basically it has multiple tags and then the dependencies between the tags. And in our paper, we use a DAG-based workflow, and we particularly focus on the task clustering, which is a technique that merges small tags into the job, and then so as to reduce the scheduling overhead and other overhead. Basically, in our paper, we argue that existing clustering strategies have ignore or underestimate the influence of failures, particularly for the test failure. So we propose 3 methods to improve the fault tolerance. That's the introduction. And then for the system overview, here we show that how we typically run a workflow in such a distributed environment. So at the beginning, we have a submit host which has all the scheduler clustering engine, workflow engine, and we have multiple worker nodes in each executing side. So at the beginning, we have a workflow. In this simple example, we have only a tags at 2 levels. So after the workflow engine will release free tags to the next level in case those tags have these tags the parent tags of these tags have finished successfully, and then the workflow engine will release these tags to the clustering engine. And in the clustering engine level, those free tags will be merged into jobs so as to be submitted to the scheduler, and then match with the resources, the remote resources. And then at the remote side, each job will be matched to the resource. In our case, it's a worker node. So, and then in this worker node, once it gets this job, it will execute these tasks in this job one by one or in parallel. And in our paper, we will talk about the sequential execution. So here's the look at the timeline. Just in the case of clustering, we have 2 tasks in this case, and we have only 1 overhead. But in the case of without clustering, we have more scheduling overheads. Yeah. So that's how we get some improvement in task clustering, because we have less scheduling and submit delay in this case. So for the task clustering, typically has at least 3 types. The first one is horizontal clustering, which is to merge tasks at the same horizontal level into the jobs, and then it's simple because in each horizontal level you don't have any dependencies between these tags, so it's simple to do this horizontal clustering. And for the vertical clustering, it's a little bit complicated because you need to merge tasks at the same vertical pipeline together and figure out the dependence. But the benefit of it is that it can also reduce the data transfer between the tasks. So the next one is 2-dimensional clustering, which is a combination of both of them. So what it does is to merge both in horizontal dimension and the vertical dimension. And in our paper, we will talk about the horizontal clustering, and in this in horizontal clustering, here it means the clustering factor, which is the number of tasks in a job. That's the focus of our paper. So because we want to see what's the optimal clustering factor in this case. So in this simple example, the clustering factor is 2 because we have 2 tasks in this job. So that's the task cluster. And then we'll talk about the failures. In our paper, we only focus on the transient failures, and we only and for those transient failures, if we have failures, we will try these tasks or jobs, and then after a few times, eventually we will finish them successfully. So, and we don't care about the cost of the failures because we only care about the average failure rate, and we want to see how the failure rate influence the overall runtime. And the assumption is made in that a failure is a random event that's independent of the workflow characteristic or the execution environment. In some cases, it may not, and we will talk about some special cases for them. And we classify the failures into 2 categories. The first one is a test failure, which means a test failed, but other tests in the same job may not fail. For example, if the failure is highly related to the application itself. And then the next one is a job failure, which means the job fails, and then all of its tasks fail as well. So if this failure is related to your scheduling system, your execution system, it could be a job failure. The idea of this paper is to figure out how to minimize the overall runtime given n tasks to run on the available resources. If the test failure rate is measurable in this test failure model, all the job failure rate is measurable in the job failure model. And the assumption is here you have many more tasks than the available resources. But after clustering, n by k, which is the number of jobs, may not be much larger than the available resources. So here are other trends that we use in this paper, including because we assume that we already know the runtime of a single task and the time delay between jobs, and then the time delay between jobs is the same for all the jobs. It's a simplification. We measure the job failure rate and the task failure rate after you finish a few tasks and jobs. So here's after some calculation we can estimate the overall runtime. The reason why we have 2 equations here is that we need to figure out whether n by k, which is the number of jobs, is larger than r, which is the number of resources. Because if in that case, if it's larger, then we have multiple scheduling circuits. Otherwise, we have only one and just one scheduling circuit. So that's the only difference. And here's the graph for the simple example with some which is close to our simulation. We can see that it looks like a valley when the clustering factor, the x-axis is the clustering factor, and the y-axis is the overall runtime. And when the clustering factor is very low, and the overall runtime is very high, because in this case the overhead will be very significant. And at the other end of the curve is also very high because in this case you spend much time in retrying your jobs. So the optimal clustering factor in this case is a constant value which is equals to n by r. And the conclusion here is that because the optimal k is independent of beta, which is the job failure rate. So in the job failure model, we don't necessarily need to adjust the clustering factor, just set it to be this optimal, and it is not related to the job failure model. Although the overall runtime will increase with the increase of the job failure rate. But for the test failure model, things are quite different. Because here's the graph for the test failure rate with the same parameter. But in this case, the optimal clustering factor is dependent of the test failure rate, which suggests us it's necessary to adjust the clustering factor based on the test failure rate that you have detected. So and we show that with the increase of the test failure rate, you need to reduce your clustering factor. Intuitively, it's true because if the failure rate is very high, you don't need to cluster that much, because in clustering will increase the risk of failures in this case. Yeah. So comparing the two models, in the case if you don't know the real cause of your failures, how do you know which model is satisfied? So the first you can see whether there's a linear increase or an exponential increase when the k is much larger, and the second one whether the second is whether the optimal clustering factor will change or not. So that's the difference between the two models. So based on the models, we propose three methods. The first one is called dynamic clustering, which is to adjust the clustering factor just based on the equation that we just get dynamically. In this simple example, we have a job which has 4 tasks, and 3 of them have failed. So in the job retry, we will divide this job into two smaller jobs, and then retry both of them. So the clustering factor is reduced from 4 to 2. The next one is called the selective reclustering, which only retry the failed test in the job. But this method requires the identification of the failed test. It may not be supported in real systems. So in the same example, we just retry the 3 failed tests and we return the successful test, but we don't change the clustering factor at all. And the third one is called dynamic reclustering, which is a combination of both of them, which means we not only adjust the clustering factor, but also we only retry the failed test. So that's the dynamic reclustering. So evaluation, basically we run our it's a simulation-based evaluation, and but we use the real chases that were run by the Pegasus group, and then each workflow was simulated 100 times so that the standard deviation less than 10% of the overall runtime. And then we use 2 scientific workflows, and they will run on 20 workloads. And for the workflows that were used, the first one is montage, which is a astronomy application that's used to construct a large image of the whole sky. It has very complex data dependencies between each other, and here's a very simplified case. The montage that we use has more than 10,000 tasks and 57 gigabyte data. The next workflow that we use is the periodogram, which is used to identify some periodic signals from light curves that arise before transiting planets. It has more tasks, but it has a simple structure which has only one level. So the simulator that we use is based on the Gaussian, but we add some components to it. And Gaussian is widely used in workload management. First thing we add is the workflow engine, which is to handle the data dependencies, and the cluster engine, which is used to merge small tasks together, and then the scheduler based on the reliability of your resources and match your jobs to the most reliable resources. And then the failure generator, which is to generate test failure or job failure based on the test failure rate that the user has specified. The failure monitor will correct the failure records, including the resource ID, the job ID, the type of your job, and send this feedback back to the clustering engine. So the clustering engine can adjust the clustering factor or use some other policies. So we compare the 3 methods with the case with no optimization, which means in this case the K is set to be M by R, which is the optimal clustering factor in case of no failures. So we compare the overall runtime. In the case of periodogram, the blue curve is the overall runtime of no optimization, and it's much larger than all other 3 methods. But if we enlarge it, we can see that among the 3 methods, the dynamic reclustering is slightly better, and then the dynamic clustering, and then the selective reclustering. So because dynamic reclustering is a combination of both of them, so that's somehow better. For the montage case, it's quite similar, just the improvement is not so significant. But still, if you see the difference between the three methods, we can see that we can draw the same, almost the same conclusion. So at the beginning, we assume that those failures are independent of the workflow characteristic and the execution environment, but in some cases they may not be. So in the case when test failures are related to the type of test, which in this case our failure monitor will classify the failures based on the type of your job, and then the clustering engine will merge this test based on the estimation of different test failure rate for each type of them. And in one simple example of montage, we set the test failure rate of two types of montage to be much smaller than the other one, and then we show whether our test specific failure detection is able to improve it, and the conclusion shows that it's not much difference, because if you go back to the model, we can see that the overall runtime is not very sensitive to the test failure rate if the clustering factor is already very small, it's already close to the optimal clustering factor. So in this case, it also suggests us that the estimation of the test failure rate doesn't have to be very precise compared to other parameters. And also shows that our simplification is acceptable in this case. So another case is the location-specific failures. In the case when the test failures are related to the location of your execution, so in this case the failure monitor will classify the failures based on the resource ID, and then the scheduler will try to order the resources based on the reliability of your resources. In one simple case, when 2 out of 20 nodes have higher test failure rates than the others, and in this example, we can see that only for the dynamic clustering we have a very significant improvement when the failure rate is very high, but for others it's almost it's very small. The reason is that because in dynamic clustering, because when the failure rate is very high, and if it doesn't have the failure detection, it will generate many small jobs, but at the same time it still cannot reduce the job failure rate because it's not caused by all of the nodes. So it will create more and more smaller jobs, and so that's why the performance will be so significant. So in the future work, we'll apply our work to the vertical clustering and then the two-dimensional clustering, and we also use more workflow examples since we only have 2 examples in this case. And we also talk about the distribution of failures, because in our paper we only use the uniform distribution in this case. So any question now?
So how much time did you have? Because you're 18 minutes and 31 seconds here. Yeah.
I should have 25.
If you have 25 minutes, then you've got plenty of time.
Yeah, so was I too fast?
Yeah, I think you were glossing on some of lot of the stuff. Like for a person who's coming to your talk for the first time, they have no idea about the approach. So maybe we can go through each of the slides.
Yes, sure.
I would say that this version is like 200% better than the previous one.
Yeah, this, yeah.
This, that said on this one, that I thought that the DAG-based model was pretty simple, but it doesn't really matter that much. And it's easy to see how this one relates to the next slide, but you know, I think it would be clearer if you had like a diamond workflow or something. A diamond shaped
okay,
workflow.
like diamond. Okay.
Yeah, I mean, you don't have to change it, but I was saying like that just looks like
Different.
it doesn't look like a DAG. I mean,
Yeah.
it is a DAG, but it doesn't look like a DAG, right?
I mean, you could easily add up one more next to it, just as another example. I mean, it doesn't have to be replaced. It could be.
Yeah.
So the other thing which you need to keep in mind, so when you started this introduction, you were saying task with scientific workflows.
Yes.
A distinction between a task and a job
Oh yeah.
is a completely a thing which is specific to Pegasus, which we are trying to draw out to, you know, clarify to users what the terminology is in the whole system. But in your talk, so you, while explaining this slide, you went quickly like there's a job and there is a task-based thing. You did not even draw any distinction.
Mm-hmm.
And you know, like when we get onto the latter part of the talk,
Mm-hmm.
you have different job and task-based failure models.
Mm-hmm.
So you need to do a better job explaining the distinction.
Yeah,
Right
right-
now,
right
looking
here.
at this slide, it doesn't.
Yeah, you should say right here, like, what is the difference between a task and a job?
Mm-hmm.
Say, you know, a task is some, you know, a unit of work that's in the workflow that the user needs to get done, and a job is, you know, something you submit to a remote
Mm-hmm.
resource.
Execution.
Yeah, or the job is how a workflow system sees it when it executes it.
Mm-hmm.
Yeah, I would say it's like a concrete instance of a task, or, you know, or of a collection of tasks,
Mm-hmm. Yeah.
an executable instance of a task.
I'll go through the animation.
No, yeah, go back to this one. So this one, I think that plot on the right side
Mhm.
is rotated weird, because it doesn't look like, I mean, it should, you know, normally in 99.99 times out of 100, the timeline is horizontal. When people think of time as being horizontal,
Yeah.
and nobody thinks of time as going from top to bottom. And so when you look at that thing, it looks very weird.
Yeah, it threw me off. I couldn't figure it out, and my view was obstructed a bit too at that
Okay.
time. As to
Okay. Yeah, I got it.
Yeah, so it needs to be.
Switch.
Just rotate it
Rotate.
Yeah.
counterclockwise 90 degrees.
Mm-hmm. Okay.
So the purpose of this slide is to give a generic overview of workflow systems,
Yeah.
or is it an overview of your setup?
Well,
Overview of actually a workflow system like Pegasus. Because in my setup is a little bit different because it's trying to simulate Pegasus. Yeah.
but you're also trying to convey the point why you would cluster the tasks.
Mm-hmm. Yeah, I try to explain why we have task clustering. Yeah. So like give you some basic, like the timelines is why the task clustering is important, because we have that like overhead stuff.
Do the
So,
next
but
step.
that should be mentioned then either in a slide which leads up to
In that
this slide.
Uh-huh.
So there should be a slide in between which says, you know, we are looking at clustering of tasks. Why do we want to do clustering?
Mm-hmm.
Because again, like you're assuming a lot of things because we do it in Pegasus and it's intuitive to people who've used Pegasus.
Mm-hmm.
But to a general audience, you know, it will take them some time to figure out why do we even cluster tasks.
Do the next step in animation, please.
This.
Oh, yeah, next one from here. So when you spoke about this, you said that they are considered horizontally already. Right?
Yeah,
You said
'cause-
like first we do this level and then we do this level.
Yeah, so
Which
it's
is-
horizontal clustering actually.
Well, but you didn't say clustering at that point. You got to clustering later on in the
Yeah.
animation.
Yeah.
Like if you go to the next step again. But here you start talking about the clustering. What
Yes.
the green stuff is a clustering.
Yeah.
right? But I mean, really, what happens when you schedule it is when tasks are ready, right?
Mm-hmm.
And that doesn't really happen at levels.
Mm-hmm.
So I mean, I would just probably say that differently. You know, I wouldn't.
Yeah, I mean,
maybe change the animation. I thought it was pretty confusing.
the other thing about this is that when you show the first transition, so go back a couple units here. So this is the DAG you start with. You
Mhm.
submit this,
Mm-hmm.
and when you click on the next one,
Mm-hmm.
it looks like the lower level of tasks. It
Oh.
looks like the lower row,
Okay.
not the first.
Okay.
You might want to leave it, go back one, sorry.
Mhm.
If you leave that picture and just color it, I think it's more clear,
Mm-hmm.
right? Don't remove it, don't move it to
Okay.
levels. Just color in the notes on this one or shade them.
Okay.
Because it's hard to follow when you keep on changing the picture.
Okay.
So the other thing which I had is like, let's say if you were to map this slide to a Pegasus context, what is the workflow in there?
But it doesn't matter. But this is
No. So the reason I am asking is like, are you saying that so jobs are released and then clustered, or they're clustered beforehand and then released?
no, they're released and clustered, right?
Okay.
That's the only way the system would work.
Yeah.
Alright.
This is not
Yeah.
Pegasus.
Actually, yeah, because I need to do some like a recastering. So that's the thing. Like, when you have some free tasks and then you cross them again
Okay.
and again.
Alright.
So that's how it's happening in the simulator. So it's a bit different to Pegasus. That's why I did not mention Pegasus actually here.
I have a comment in my notes that later on you do mention Pegasus, and my question for you is why are you even mentioning Pegasus in this talk? In one of the future coming up slides, I don't have the slide number, but you mentioned Pegasus.
Yes, I just say that like the traces, the input data is generated by the Pegasus workflow management system, somehow like that. Because that's probably the only place that I mentioned Pegasus.
Okay.
Yeah. So actually it's quite similar to Pegasus, but not the same because I cannot do something in Pegasus. Yeah.
It actually relates to the diagonal replacement kind of thing.
Yeah.
Yeah.
Yeah, so this here, I think these task clustering slides should go before the system overview.
Uh-huh.
Because here you explain what you show in the previous slide.
Mm-hmm.
So here you're saying how clustering works.
Yes.
In the previous slide you're showing what the mechanics of it are.
Mm-hmm.
So I think you should describe the
Yeah.
concept first and then how it plays out.
Okay. Yeah. Yes.
And then the other thing about this one is that you do two-dimensional clustering, but it's not really two-dimensional clustering. It's sort of like label-based or
Yeah.
arbitrary clustering.
Yeah, like, but what's a better term? Like, I mean, if it's labor clustering, it sounds like you're clustering manually by labeling. Right.
You are clustering by label. In Pegasus is label-based clustering, but it's really an arbitrary clustering. It's
Mhm.
not just, I mean, it is kind of two-dimensional if you think of horizontal and vertical dimensions,
Mhm.
but it's like, I think, you think of a box or something, you think 2D, but this isn't really a box,
Like
it's
block,
it's a subset
block,
box.
box.
It's not a box, that's what he's saying.
That's what I'm saying, it's not a
Don't
box.
think about it as a box.
Like,
Mhm.
for example, when you get down to the two-dimensional clustering and you hit forward twice or whatever, there.
Mm.
See, you're showing two squares here, but it doesn't have, it could be the top two of that one and the bottom two of that one. Well, that's not a valid clustering, right?
Yeah, I mean, but it's just like if you want to optimize the all around height, it will be something similar to this one.
Yeah, but what I'm saying is, like, I would just, I don't know if I would call it two-dimensional clustering. I would call it like arbitrary clustering.
Mm.
But you're not considering it anyway.
Actually, not in this paper, but like in another paper I talked about.
Yeah.
Because in another paper, it's more likely to be two-dimensional clustering rather than arbitrary or labor clustering. Because in that case, it's like a combination of horizontal and vertical. So that
It's really some graph, not letter.
Yeah, I mean, so that I'm just saying, like two-dimensional, you know, sort of to me when I hear it, I think of like contiguous, like regions or whatever. It could be some arbitrary, you know, subset of the graph that's valid. So I think the point is to get across that it could be any collection of the nodes that you put together, as long as they don't depend on themselves. As long as you maintain the DAG, right?
Yeah.
So that's the important bit.
So I replace it by arbitrary clustering.
Well, I'm just suggesting that you call it something other than two-dimensional clustering. I'm saying you have to. I'm saying you should think about it.
Yeah.
And because the point of the two-dimensional clustering is that you're combining the horizontal and vertical, but you're not just combining horizontal and vertical. You're combining sort of an arbitrary. It's like the catch-all. It's like the superset of horizontal and vertical. It's not just two-dimensional. It's like any valid clustering. So if you go back to the previous slide, I want to look at this because I didn't see. Okay, yeah. I think this K, because I didn't see this slide because it was chopped off there, but on the definition slide, which I think is the next one maybe, you should say what K is, because it says K one time on that slide. So if you go to the next slide. Not this one, the next one.
Next one?
Yeah, this one. So you say K right there,
Yeah.
and then you show a little table below this,
Yeah.
but it doesn't have K in it. Or it does, and it's
No,
not.
no.
So I think you need to put K in that table.
Okay. Yeah.
And put, I would put the table above all the description or whatever.
Go down.
I think this slide's kind of clear.
So here, I heard your talk for the first time. So one thing which I found a bit surprising was, so you don't make an attempt to explain the equations in English at all. You just say, here's some equation, that's it. And at this point, like again, you have all these factors referred to by acronyms. I've already forgotten what means what. Honestly, like I was totally clueless. Like my general suggestion is, like, wherever possible, you should try to have the legend of what each parameter means, because like if you go back to your previous slide, you have like 7 different.
If you just take that table and made it a little bit smaller and put it up in the corner of the next slide, it would be.
Yeah. So in all of your equation slides, you should have some sort of legend which allows the user to get to it, and then also when you talk about it, like try to explain the equations a bit as to what they are looking at.
Yeah.
Like, when you're doing that, you didn't.
So I still have plenty of time.
Yeah. So I think that would be very helpful to understand.
So let's see that graph, the next one. So what's the magic with 50?
Because K, optimal K is M by R. In this case, M is like 1,000.
So in this case, it just happened to be.
Yeah, it's just in this example. It doesn't mean that it's like. It's just.
I'm still surprised with how the graph looks.
Huh?
I just can't figure it out, I guess. So runtime goes down.
Maybe I should
So
point it out.
clustering factor is the number of tasks in a cluster, in a job, not the number of jobs.
No, I understand that.
Because the number just doesn't really matter in this case.
Number is the same. And what's the expected runtime? It's the runtime for the whole workflow, or?
Because in this case, it's like you have like 1,000 tasks without dependencies, so it's workflow or workload, whatever it is. It's just a simplification of calculation.
So what happens at 50 is you cross that boundary where,
Oh, because in this case, that's why I say that there are like two equations, because here you have multiple scheduling circles, but here you have only one scheduling circle. It doesn't change, even though you may have less and less number of tasks.
So I think Karen is right. If you would take that example and just kind of show how you get that graph,
Mm-hmm.
like not walk through maybe everything, but just saying try. Then you will both explain the equation and that graph a little bit.
Yeah.
you can say, at low clustering factors, this is what happens. The overhead is high, so the expected runtime, and then it pretty quickly gets down to close to an optimal clustering factor, and then it starts, at the point where you get, one scheduling cycle, then the failure rate starts to go up, or the runtime starts to go up because, you end up re-executing.
Exactly. That's the key point there, right?
Yeah. So like.
Yeah. So the reason why it goes up at that end is because of the overhead. The reason why it goes up at that end is because of the failure rate.
Yeah.
Because the jobs are more likely to fail.
I think this is probably one of the more important ones to actually get right. Because if you explain this correctly, a lot of the stuff that's coming after this just falls into place. So this one I would probably practice a couple extra times.
Yeah, and the next one, the task failure, because I think it's also important to say, like, you explain the job failure model, then you explain the task failure model,
Yes.
and you say, because of the optimal K is independent of alpha in the job failure model, you're not really considering job failure model in your experiments.
Yes.
And so I think you need to say that again at the end of this before you start going into the three different approaches. You got to say, so considering only the task failure model and setting aside the job failure model, because there's nothing we can do about the job failure model. We just pick the optimal K and we go on, right?
Yeah.
We can calculate it a priori without, whatever. It's going to be the same regardless of what your beta is or what your alpha is. So we just calculate that. But for the task failure model, we have these three different options that we tried out, different approaches for what you could do.
Yes.
So.
Yes.
So this one to me, like you made the comment in the talk that, the job failure model, K is independent of alpha. Here you say it's dependent on alpha, but to me, looking at that, I see a couple different values for alpha, and I say, why wouldn't I just pick that lower clustering value?
So you said.
Because it looks like those lines converge at a minima right there.
Yeah, but the thing is, if you look at this graph, you can see that actually, yeah, you can put any. If you put like a 10, 20, it's almost the same the overall runtime. So the only thing we need to do is, if there's no failure, you should put it 50. But if there's failure, you should reduce it. But it doesn't have to be very precise, like whether it's 20 or 21. But just reduce it from 50 to 10 to 20. That's it. That's enough.
So So you're going to say it's dependent on alpha, but it's not sensitive.
Not sensitive.
Right.
Yeah. So, because otherwise the optimal would be this one. But if it has failures, you should reduce it to that to the more failures.
See, I don't get when you say it's optimal is 50, because it looks to me like 50 is not the low point in that graph.
And not in this graph. In terms of no failures. But if the alpha is much lower.
So maybe you should put a plot on there that says alpha equals 0.
Yeah, somehow. Because if this alpha is 0, it's almost like a curve like this.
Yeah, it's flat from the bottom.
Almost flat.
It's flat until you get to.
So it will be. Optimal will be test 1.
Yeah, it's flat until you get to 50, and then it starts going up. But
Yeah.
it starts going up because now you're limiting your parallelism.
Yeah.
in the order of these three methods, I would do first selective reclustering, then the third one, that dynamic reclustering, and then I'd say that because it's hard to figure out which job
Yes.
failed, therefore we need to do dynamic clustering.
Yeah, that sounds more natural.
In this example right here, you go from one job to two, but you could also go the other way, right? From two jobs to one.
In reality, it's not very possible because all you need to do is to reduce it from 50 to 10 or 20 in most cases, because at the beginning you don't have any record of failure, so you set it to be 50 because you thought it would be the optimal clustering factor. But when you have more and more failures, when you become more and more the failure rate increasing, you will reduce it. So in most cases, you will have much smaller jobs. Yeah. Because I think.
So what you're saying, when you encounter a failure, you're going to decrease the clustering factor, not increase it.
Decrease, yeah. Because I can show you there's something I skipped at the end. Because that was not mentioned in this, but in this place, so actually it will only in most cases it will only decrease. Yeah.
So this one, you said when you were going through the slide, you talked about each of the things. You said, oh, this workflow engine does this, clustering engine does this, and the scheduler does this. And you said, when you talked about the scheduler, you said more about how it chooses the most reliable resource than actually, what, I don't understand what it, otherwise, is that the purpose of the scheduler? Is it to match it to a resource? Is it to match it to an available resource? Or the available resource with the best failure rate?
Because by default it doesn't do that, but in that location specific failure detection, the scheduler has to do so as to match a job to more reliable resource, because you have an order based on the
yeah. So I would just say here that the scheduler, I wouldn't mention that because that's going to confuse people until you talk about the other thing.
Yes.
I would just say here that the scheduler matches the clustered jobs to available resources for execution.
Okay. Yeah. That's good.
So, again, in general for these slides, you have enough space to expand on that acronyms or have a written for that.
Actually, it seems very simple to me.
Okay.
I think it's pretty simple.
Yep. Yep. Because simulation, they hide many details for you. The result seems very ideal. Very,
Well, the thing I would point out here is if you go back to the previous plot, I would say the no-op, that's the way it's done now. And I would make a strong point of that, because that's the main benefit to the approach that you're talking about, is that the status quo right now is to do this no-op, which does terrible if you have failures.
Yes.
Right? Even low failure rates, right?
Yeah.
So there, the maximum failure rate there is 1%, right?
Yeah.
So you gotta say, like, even with a really tiny failure rate, the runtime, crosses, like an order of magnitude or something.
Mhm.
So make a point of that. Say, like, no matter what of my approaches you choose,
Mhm.
it's infinitely better than the way it is done now.
Mhm. Yes. That's actually true, because if the failure rate is higher than like a few percent, then the
Yeah.
simulator
It doesn't finish. It doesn't make progress.
finish.
And this one, so your conclusion here is that
It doesn't matter.
it doesn't matter.
Yeah, because in the case of montage, because even though like the failure rate is like only like a 20% difference between the real case, it's still acceptable. Because if the only thing you need to do is to decrease the customer rate, just not make it so high, and that's already, if like there's not much difference between 10 and 20, but there's much difference between 10 and 50.
Yeah.
That's the only thing.
Yeah. So I think the overall point of this whole paper is that you need to make sure that everybody who's listening, even if they're not paying attention, they're checking their email.
Mm-hmm.
The one thing you got to say is, like, the main takeaway
Mhm.
is that if you have to do some kind of dynamic reclustering to deal with failures.
Mhm.
If you don't do that, then the runtime's going to suck.
Mhm.
But if you do that, even a basic one,
Mhm.
then you'll get much better results.
Yes.
And if that's the only takeaway that people get, then I think you've won.
Yeah. Because actually my model is very simple. It doesn't really consider many details. Yeah. But still, if you have it's already enough to improve. Of course, there are much more space to do more, but it's already good enough. Yeah.
So now, in that previous case, does the scheduler, when it's ordering based on failure rate of the resource, does it reject at a certain threshold? Does it say, okay,
Yeah.
it does.
But it's like set by the user. If you don't, if you say like more than 50%, if it fail, just skip it. It's just set by the user.
So, but do you have some automatic way of setting that?
Not
Can
yet.
you say, like, there's a way to calculate it, but I haven't done that yet?
Not yet.
Yeah. So, maybe that's a,
Yeah, this is a extension. I mean, that could be done.
yeah, say, like, the scheduler can in the future, if it knows that a resource is bad, not send jobs there.
Mhm.
Based on, it makes an intelligent decision. It doesn't just say, like, there's some threshold set by the user,
Mhm.
because the user will never set the correct threshold. It would say, like, knowing what it knows about the workflow and the failure rate, and what the failure rate of that resource is,
Mhm.
they can say, like, send this job there, but
Mhm.
don't send that one there, or something.
Yes. And just probably.
One of the ways that to drive home that point that they didn't see is maybe to have a conclusion slide.
Oh, conclusion for
Yeah,
for the whole.
yeah,
Okay.
like what he said about
Okay.
what he just said.
Yeah. Yeah, I know that.
Yeah, so I would say, so that's the main conclusion.
Mhm.
And then I would say a secondary conclusion is, you want to do this dynamic reclustering, right?
Yeah.
Is the best one,
Mhm.
but you can only do that in certain cases, right?
Yeah.
And so you should say, like, this is the best one, but you can only do that if your system supports this.
Yeah.
Otherwise, use this one,
Mhm.
and then even if you can't do that one, then do this one.
Mhm.
But regardless of what you choose, then if you do one of them, then you're gonna get a big win.
Mhm.
And I think that would be the whole conclusion slide, basically.
Yes.
It's good. This is a lot better than the last talk. it's much more clear. I don't know if that's just because we sat through the other talks, but I think you thought it, well, I mean,
I
you don't
wasn't
have
there.
anything compared to, but it was mostly clear.
When was that talk actually?
When you was on vacation or?
Yeah, I think you were in
Boston.
you were somewhere. You were on travel, I think.
Yeah. Cool. Thank you all.
No problem.
So when is your talk next week?
Sunday. This Sunday.
Oh, this Sunday.
Sunday?
Yeah.
It's a weird day.
Yeah. They usually put workshops before the general conference.